All right, so we were covering the discrete cosine transform under the topic of general broad topic of transforms, image transforms. And we said that the discrete cosine transform is an optimized transform, particularly for autoregressive one sequences with strong correlation between pixels, between neighboring pixels. And we apply it in a fast manner. There is a fast implementation for that. But because of the availability of the discrete cosine transform, particularly for autoregressive one sequences, we further said that we should better apply it to images horizontally or vertically and vertically, but only along a region where this autoregressive one assumption holds. Otherwise, if it doesn't hold, if we don't have that kind of an assumption, DCT does not perform well. So that's why, for instance, the JPEG compression standard first splits the images into 8x8 blocks, smaller blocks, where we can assume that the image within that small block, at least, will have this kind of a layout with the autoregressive one structure, and the pixel-wise correlations are large, so we apply JPEG to that. And JPEG is an interesting one. I want to talk about it a little bit further, like after splitting the image into these 8x8 blocks, so each of them are 8x8 smaller images. So this is now the image itself, we can say, like this. It's a very small image, as you see, but it is pretty much uniform. The pixel values are very much correlated. So we apply DCT to that. That makes, let's say, the top corner to be a large value and the other pixels, not pixels, coefficients, let's say, have smaller value, and it's real valued. So in order to make it in the correct descending order, a zigzag ordering is applied, which converts this 8x8 matrix, let's say, into a length 64 sequence, the first being large and the second being small, etc., and it's getting smaller and smaller, like this, in magnitude, of course, in magnitude of x. It may be negative or positive. And after the reason of doing this is just to, for example, find the point first where the rest can be assumed to be zero, quantized to be zero, and the others are quantized. The quantization is a simple process. It just divides by some number. You have a value, okay, a value of x. You divide it by a number, and it becomes a smaller value. And then you truncate it to make it an integer. For example, if your value over there is, if the coefficient over there is, let's say 5, and the quantization performs by dividing it to 7, let's say, then 5 over 7 will be something smaller than 1. And when you truncate, make a round of, not a round of, but a truncation operation, it becomes 0. So more values become 0 like that with the quantization. And after the quantization, some integer numbers are obtained, an integer sequence. And this integer sequence is further compressed using some lossless compression methodologies like Huffman coding, etc. It's like zipping your file, compression of your file. So we have a lossless compression, and we have therefore a representation, and the beginning of that representation and the end of that representation is added with a header, the representation, and the trailer. So this thing is the bit stream that you construct for representing all of your 64 pixels, 8 by 8 pixels, and you patch it over there. This is not an image standard, but it's a compression standard, and you can use it by compressing for compression of images using other image file formats. So we don't specify a file format here, we just specify the compression. If you put the header of a file format, let's say tagged image file format, which is abbreviated as TIFF, then it will be encapsulated within TIFF, but the compression parameters are just JPEG descriptors. The lossless compression standards and this quantization table are all specified in the JPEG standard. You just make the quantization, which is formed by division by numbers. By making those numbers, you compress more because more of the numbers will become smaller and smaller and will be zero. So the quality setting is obtained by this quantization, by these quantization Q values as well. If you decrease the quality, it means you are increasing your division table, quantization table. And if you say 100% quality, which is the highest quality, that would correspond to division by 1, which means you're not dividing anything, you're just keeping them as it is. So it is almost lossless, except for some very fine quantization effects by losing some of the decimals. It's not perfectly lossless, but it is almost lossless if it is 100%. So this is how JPEG works. And as you see, it's complicated. It's not very simple. Even for the smallest patch of 8 by 8 pixels, we did a lot of things and we came up with some numbers. We write it on the file or we transmit it. And the decoder side just decodes this by doing inverses of these operations. It's multiplying with the quantization table. It's putting everything into the zigzag manner of 8 by 8 blocks, and then taking the inverse DCT and constructing a patch of 8 by 8 pixels and rendering on that portion of the image. And you have to do it again and again for every image. That's a cumbersome process. So JPEG is not an easy standard. Luckily, nowadays, they are doing these things even inside the microchips. But it's not trivial. It's not like putting the pixels one by one. Now, so much for the discrete cosine transform. I will open a new page and I will continue with some rectangular transforms. I don't know the name, whether it's rectangular transforms or anything, but I tend to give it like rectangular box-like transforms. Transforms. I call it this way because of the basis functions to contain rectangular boxes and such shapes instead of sinusoids. Remember that transformation is the construction of bases. What are the bases that we are going to use? If the bases are impulses, then it corresponds to time domain or space domain. If it corresponds to sinusoids or waves, then the transformation, the corresponding coefficient transformation will be a Fourier transform. If it is sinusoidal cross multiplications of cosines, then that would correspond to discrete cosine transform. There are several other types, but particularly for these types of transforms, the basis functions are essentially box-shaped, rectangular box-shaped. For example, Well, the example is the box shape itself, but the transforms that we will have will be easy to implement because they don't require multiplication. Then if it's in the form of a box, it's either 1 or 0 or 1 or minus 1. So we just add or subtract some of the values. That's how we will be implementing these transforms. And that's a nice thing. That's a very good thing. The first one that we will see is the Hadamard transform. And the Hadamard transform is recursively obtained by making the transformation matrix larger and larger. For instance, the first Hadamard transform, which is the smallest one, would correspond to a 2 by 2 transformation because that's the smallest transform matrix that you can have. Let's call it H sub 1 matrix, and that is equal to a 45 degrees rotation, 1, 1, 1, minus 1. Why did I say 45 degrees rotation? Because every transformation is a rotation, I told you before, and in 2 by 2 matrices, the transformation, let me indicate it clearly, the transform will be equivalent to a rotation, and that rotation matrix is cosine theta, sine theta, sine theta minus cosine theta, which would correspond to a rotation by theta degrees. From geometry or from trigonometry, you may remember this. So a point xy, when it is multiplied with this matrix, would be rotated by 45 degrees. Now, why are we rotating particularly with 45 degrees, not any theta, but theta is equal to 45 degrees? That is something that I want to mention about while we are optimizing, but I want to briefly talk about it a little. This rotation that we are applying essentially corresponds to the axis, with the horizontal axis being one of the directions or one element of the of your data. Your data is x and y, for example. The horizontal is x, the vertical is y, let's say. Okay, so we have 2 pixels or 2 samples, and we put them on an n-dimensional space, with each axis being 1 dimension. So this is, let's say, x, this is y for the point xy. If these x and y are strongly correlated, if the correlation coefficient is close to 1, notice that when x is large, it means y is large. When x is small, y is also tending to be small, because there's a cross correlation, high cross correlation among them. And if x is negatively large, for instance, y is also negatively large, because they tend to have a similar value. They attain similar values. So if x is, for instance, this, a large value like this, y is also some large value. If x is larger, then y is also larger. If x is smaller, y is smaller, etc. So let's put these points of x, y with a red dot here, and let's make some experiments. In those experiments, we happen to see that we come up with an ellipse-like shape. Of course, x and y are not exactly the same because they are random processes. If they are exactly the same, then it would correspond to a line. But they tend to be within an ellipse. If the correlation is large, then the ellipse will be narrower. If the correlation between x and y is loose, then it tends to become a circular or a fatter ellipse like this. But certainly it's along the 45 degrees line. The direction is that way. And if there is a negative correlation between x and y, then it would be minus 45 degrees related, because it means if x is negatively large, y is positively large, because that's a negative correlation. Nevertheless, if we have strong correlation, we have this kind of a thing, and suppose that you want to chop off one of the coefficients after the transform. We want to rotate this into an x prime, y prime, and we want to eliminate one of them for compression purposes, let's say. Then what is the best rotation that we can have so that when we eliminate one of them, we get minimum amount of error? And that is exactly the 45 degrees rotation, like this. This would be x prime, this would be y prime. Now, as you see, if you just chop off y prime, it means it's not on the ellipse anymore, but it will be on the 45 degree angle. For example, let us zoom to this particular point, red point. So by losing y prime, it would be transformed or chopped off to contain a value at this point. So how much error did we make? We make this much error. The error is this, okay, which is very small. And we can obtain that kind of an error only by 45 degrees. There is no way that this ellipse is in another angle, like in 30 degrees, in 15 degrees, or 65 degrees, or anything like that. It never happens because of stationarity assumption. What I mean is that x is correlated with y the same way as y is correlated with x. So this is transpose symmetric. And we are also assuming that the variance of x and the variance of y are the same. One of them is not significantly larger or smaller than the other one. That makes only 45 degrees reasonable rotation. And interestingly, or naturally, that's why the 2x2 transforms in any known transform, including the Fourier transform, the discrete cosine transform, and the Hadamard transform, and all the other transforms, is this 1 over square root of 2, 1, 1, 1, minus 1. That is always the same transform for 2x2. The transforms start becoming different at larger sizes, like 4x4, 8x8, etc. When they become larger, they tend to show different properties. So this is the 2x2 Hadamard transform then, and it's also the 2x2 Fourier transform and everything actually. And we recursively generate the other sizes, for example, H2, by using H1 and inserting them in a matrix with the same sign layout of the 2x2. Like H1, H1, H1 minus H1. What is H1? It's there. It's the 2x2 matrix. So we insert that 2x2 matrix inside our matrix, and we form a 4x4 Hadamard transform, which is 1 over 2, 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, 1, 1, minus 1, and the negative of these four, which is minus 1, minus 1, minus 1, 1. So this is the 4x4 Hadamard transform. And in general, we recursively go on like this by saying that Hm for any m is equal to 1 over square root of 2 Hm minus 1 Hm minus 1 Hm minus 1 and negative of Hm minus 1. So as you see, for instance, H3 will require utilization of H2 inside it, 4 of them, and it will become an 8 by 8 transformation. By the way, I want to write that example of H3, the 8 by 8 Hadamard transform. There is, every time you increase the size, you multiply further with a scale of 1 over square root of 2 to make sure that the column or row vector magnitude is still kept to be 1. Okay, the orthonormal transform is achieved that way. So H2 was with a coefficient of 1 over 2. We have now further square root of 2, which makes it 1 over 2 square root of 2. And inside it, I'm going to render the H2, which is already 4 by 4. What was it? It was 1, 1, 1, 1. Sorry, minus 1. 1, 1, 1, minus 1. 1, 1, 1, minus 1. 1, 1, 1, minus 1. It would be a little bit long. Sorry about that. And the same. 1 minus 1. 1, 1. 1 minus 1. 1 minus 1. And the same here. 1, 1, 1, 1. 1 minus 1. 1, 1. I'm doing a mistake here. I'm sorry about that. These should be negatives. I just forgot to negate the bottom right corner. So it will be 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1. And the negative of all these 4 by 4 things. And that would be minus 1, minus 1, minus 1, minus 1, minus 1, 1, minus 1, 1. And minus 1, minus 1, 1, 1. Minus 1, 1, 1, minus 1. So that's an 8 by 8 matrix. There's one drawback or flaw in this construction, although we don't technically require it that way, but to be implementation-wise simple, we would require from top to bottom to produce a basis which will depict the highest energy from the top to the lowest energy at the bottom. And that usually happens with the ordering of the frequency. If the first one is a DC, for example, which is a DC, by the way, then we want the bottom one to be the highest frequency. So the frequency is expected to increase in rows and similarly in columns as well. But what I can see at this point is that it's not working that way. The frequency for rectangular box shapes is a difficult concept because frequency is related to sinusoids. But this one has a different terminology. So from frequency, we have to proceed to so-called sequency, which is related to the number of sign changes or rectangular edges. So let's say a number of sign changes. So how many sign changes do we have? That would correspond to the sequency. For example, the frequency of the first row is 0, which is the DC, and that's nice. It's at the correct position at least. Now let's count the number of sign changes in the second row. It is 1, 2, 3, 4, 5, 6, 7. There are 7 sign changes here. Probably the maximum, the highest number of sign changes. That is a place, that's a row which must be pushed all the way to the bottom. So the bottom one should be this row, actually, in practical applications. And the next one is 1, 2, 3 sign changes. And the next one is 1, 2, 3, 4. The other one is 1. The next one is 1, 2, 3, 4, 5, 6. That's also a lot. And then we have 1, 2 sign changes, and then we have 1, 2, 3, 4, 5 sign changes. So these are the sign changes, and we should better shuffle these rows to their correct positions. That would be a more meaningful and probably helpful transformation for energy compaction, which will eventually make the first terms to contain larger magnitude than the final terms. If you make the shuffling, the correct shuffling. If you don't do the shuffling, you have to be careful about which is where and things like that. But the construction is like that. So you may want to correct the ordering, and then it becomes the actually used Hadamard transform, which is also known as the Walsh-Hadamard transform. Okay, and it's simple. A good thought experiment, an algorithmic exercise, is to find a way to automatically correct the ordering. So what is the actual order that we should push these, the second row, for example, to the last, and etc. in their correct order, the 0 being the first, and then 1 being the second, then 2, then 3, etc. Because there's an algorithmic way of deciding it. For example, for H3, it happens to be like this, but for H4, that would be a 16 by 16 matrix. It's getting larger, and then 32 by 32. Can you tell me what are the orderings of the 32 by 32 matrix? Can you find it without finding the matrix? Can you inspect the correct way of ordering that one? It is related with the binary representation of the ordering numbers, which is 3 bits, as you see. For from 0 to 7, there are 8 values, and you can represent them with 3 bits. Just focus to those 3 bits and determine the rule. By the way, for the H2, the 4 by 4 Hadamard matrix, let's write the order. This is 0, this is 3, this is 1, and this is 2. Look at the orders. So the rule must hold for any Hadamard transformation, larger or smaller. If you can find that rule, it will be easier to make the correction. And that would be a nice thought experiment. Who knows, maybe I may ask it, which means you may want to look for methods to do that in the literature as well, in the books. Maybe there is a way. But before finding the rule, it may be a good exercise to first think on it a little bit, and maybe you can also find it. Okay, and the last box transform that I want to talk about is called the Haar transform. The Haar transform is quite different from the Hadamard transform. It's quite different from the other sinusoidal transforms too, because when you look at the basis functions or the basis images, which are the outer products of the basis functions, you take a basis function. A basis function is, let me go back. A basis function is, for example, one row. Another basis function is another row. You take the outer product of those two basis functions, two vectors, two rows, and you come up with a matrix. That matrix is a basis image. So for these 8 basis functions of the Hadamard transform, how many basis images do we have? We have 8 times 8, which is 64 basis images. Just like the basis images for the discrete cosine transform that we have seen. So DCT and Hadamard actually look alike. The last basis image would be like a checkerboard. It will not be like a checkerboard. It will be a checkerboard. And the first basis image will be a flat plate and everything in between. Just type on the internet the basis images of Hadamard transform or the basis DCT basis images and things like that. You will see a lot of graphical illustrations of those basis images. We construct basis images like that, and in that case, Hadamard and DCT are quite similar. But Haar transform basis images are different, and the Haar transform is quite different in terms of basis functions. The reason is that the implementation of the Haar transform is not by constructing a matrix and multiplying a vector with that matrix, which is the normal way that we know. But Haar transform actually does not work like that. It works in a different manner. And I will just try to inspire how the Haar transform, let's say, of 8 by 8 case works by example. Because I think it's more meaningful than giving you a formula for the Haar transform matrix. So the Haar transform matrix by 8 by 8, we are using again H, so you have to tell me what H this corresponds to. It may be the Hadamard or the Haar transform. And the 8 by 8 matrix that we are going to have will be there is a 1 over 2 square root of 2 to make sure that the norm of the vectors that I will write on the rows will be 1. That would make an orthonormal transform. And it starts by splitting the information or the frequency content of length n sequence. Here, length n is length 8. By splitting the length 8 into positive and negative parts to come up with an equation, like we first have the summation of two terms and then the difference between two terms. So we will have a plus b equals something and a minus b equals something, from where we can resolve for a and b. We can solve for a and b. So we have 1, 1, 1, 1, 1, 1, 1, 1, which is the DC at the top. And then we will split it into two sections of left and right and say that the left-hand side is positive and the right-hand side is negative. When you multiply a column vector with these rows, the first row is therefore going to give you the summation of all those values divided by 1 over 2 square root of 2. Let's forget about that. It will be the summation of the coefficients. And the other one is the difference between the first part and the second part, from which you cannot find these 8 numbers. Okay? But in order to make it resolvable, we have to further resolve the left-hand part 4 pixels and the right-hand side 4 pixels separately. And it's going to be like this. I will resolve these 2 to the left and 2 to the right by putting 1, 1 to the left and minus 1, minus 1 to the right. But I'm going to use zeros here because this line I will only use for separating between the last, the first part and the second part of the first 4 samples. And in order to make it orthonormal, this shouldn't be 1, 1, minus 1, minus 1, because when I do it that way, the norm will be less, actually. Square root of 2 divided. So These are not 1 and 1 and minus 1 and minus 1, but instead they are square root of 2, square root of 2, and minus square root of 2, minus square root of 2. If you multiply this line with 1 over 2 square root of 2 and find the norm, you will see that the norm is 1. But I didn't touch the right-hand side for pixels or for samples. So let me do it now without touching the first 4 items. With these 2 new equations, 2 new lines, I'm able to resolve between the first 2, the second 2, the third 2, and the last 2 samples. But I couldn't resolve between these samples. It's in the form of couples. So how can I resolve, for example, these between? I have A plus B, but I don't have A and B. So for that, I need to have I need to have a difference between A and B as well. So I will put that. So what I'm going to do is like this, but I will erase. So be careful about that. I will put 1 minus 1, 0, 0, 0, 0, 0, 0, and then 0, 0, 1 minus 1, 0, 0, 0, 0, and then 0, 0, 0, 0, 1 minus 1, which is just separating all those things that appear in a combined manner. 0, 0, 1, minus 1, like this. Well, the problem is again in terms of norms, because if I put 1 and minus 1 and with a coefficient multiplication of 1 over 2 square root of 2, the norm will not be 1. And to make it 1, I'm not going to use 1 and minus 1 here. I'm going to use 2 and minus 2. 2 and minus 2. Because only then these rows will be having a unit norm. So the splitting is actually like this. First you have a DC, okay? Then you have one lowest frequency. Then we have 2 higher frequencies. Why is it higher frequency? Because one of them is 1, 1, 1, 1, minus 1, minus 1, minus 1, minus 1. But then the next one is 1, 1, minus 1, minus 1. So the width of the box shape is essentially narrower, okay, here. So that's a higher frequency. Then, but the number of rows that I use for that is twice. And then I use 4 higher frequencies. For instance, how do you make a 16 by 16? You will have a DC, and then you will have 1 positive, 1 negative sides, and then you will split each of the positives and the negative sides into 2, but you will have 2 of them. Then you will split each of the positives that are remaining and the negatives that are remaining into 2 parts. But now you will have 4 of them, and finally there will be still positive and negative remaining couples. So to split them, you will have to use 8 more higher frequencies. That's how you construct this Haar transformation matrix. It's not very complicated, but it is complicated enough. And the thing is that we don't implement it this way. So the implementation is not by matrix multiplication. The Haar transform is implemented by something called filter bank. It's like this. We have an input, x. We filter x with h0 and downsample, and h1 and downsample for a 2x2 transform. For the 4x4 transform, we further process the output of the H0, the low pass part, and split by filtering and downsampling. For example, if X is length 4, you make it 4 periodic, okay? Repeat those 4 values and make it a periodic sequence. X is periodic by 4, let's say, here in the structure. X is periodic by 4. If you filter it with something, the filter output will also be periodic by 4. That's linearity. And then you downsample. When you downsample something periodic by 4, it makes it periodic by 2, okay? So you have, let me write it in a different color. You have 2 samples coming from here, 2 distinct samples, because after downsampling it's periodic by 2. So you have 2 samples also here, and then you filter it, it will be again periodic by 2, and then you downsample it, it will be periodic by 1. And therefore you will have 1 sample here and 1 sample here. And when you add these 1 sample and 2 samples, it makes 4 samples. The input was already sorry. Are you still with me? Because I was kicked away from the system. Okay, now I came back. Okay, so it's a 4 to 4 transformation. That's what I'm saying. And the implementation is done like this for a 4x4 hard transform. If it is an 8x8 further, let me erase, further filtering with H0 and H1 and downsampling like this. If this is periodic with 8, this will be periodic with 4, so we will have 4 samples from here, and this will also be periodic by 4. Therefore, after filtering and downsampling, here this will be periodic by 2, and this will be periodic by 2. The top one, after filtering and downsampling, will obtain periodic by 1 samples, and 1 plus 1 plus 2 plus 4 is also 8. So this will be an 8 to 8 transformation. This is the way to make the implementation of the hard transform for H0 to be equal to 1 over square root of 2 and 1 over square root of 2 filter, and H1 to be 1 over square root of 2 and minus 1 over square root of 2 filter. With these 2 filters, it's the same H0 and H1 throughout this system. We make it larger and larger hard transformation. Okay, this is the way to make the hard transform, to implement the hard transform. Not by constructing this matrix that we have. Okay, it was a little bit slow. Okay, but nevertheless, this transformation matrix can be considered as the hard transform. There are several other transforms that can be constructed, but we are not going to each and every one of them. This is not a transformation course. This is just image processing. So we have seen some important ones, one of them being the Fourier transform, the other one being the cosine transform, and then 2 rectangular shaped transforms. called Hadamard transform and the Haar transform. Now I want to give a break until 10:45, okay, 15 minutes to 11. And at 10:45, we will meet again, and I want to show you one very important strategy or methodology to construct an optimized transform. These are typical transforms, but you can construct your own optimal transform for your signals. If you can find the stochastic behavior, the autocorrelation behavior of your signal, according to that stochastic behavior, you can optimize your transform and you can use it. So how can we make an optimization of that transform? That's a very critical lecture that I recommend to all of you guys to listen to. That's critical. And it also explains a lot of things regarding why transformation is good or it works in images or in signals in general. So we will meet at 10:45, okay, for a very important lecture. Until then, take care, and I'm leaving. Do you have any questions, by the way, regarding these? If you don't have questions, then we will meet at 10:45 and we will continue. So